Hi, my name is Angshuman Karmakar and I am from Leuven, Belgium. Today I am going to talk about constant time discrete Gaussian sampling for lattice-based cryptography. This is a joint work with Sujoy Sinha-Roy, Oscar Riperez, Frederick Vercauteren and Ingrid Verbahuede. Consider the above two sets of linear equations. In the left, the secret values can be easily found using Gaussian elimination from the set of known values. But in the right, the Gaussian elimination doesn't work. As the small errors that have been added to the right hand side of each equation grows larger and larger in each pivoting step. It has been shown that this problem, known as LWE or learning with errors, cannot be solved even using quantum computers. This is why LWE is a very popular choice for constructing post-quantum cryptography. Usually these small errors are sampled from a narrow discrete Gaussian distribution, mainly for better proof of security and small signatures in lattice-based signature schemes. A popular choice for sampling from discrete Gaussians is Nu-Theo sampling. It first creates a discrete distribution generation tree using the probabilities of different values in the distribution. The sample values are placed in the leaves of the tree. To generate a sample, a random walk is performed from root to the leaves of the tree. Let's see how. Starting from the root, we generate random bits. Depending on the bit, we either choose the top or the bottom branch. Here our first random bit is 1, so we choose the lower branch. The next bit is 0, so we choose the top one. The next bit is 1, so we choose the bottom branch. And now we have hit a leaf node. We stop the sampling here and return the value in the leaf, which is 2, as the sample. Now consider these two random walks, marked in blue and green. It is clear that the number of steps to generate these two samples are not equal, or the sampling process is a non-constant time operation. Currently, almost all the discrete Gaussian samplers run in non-constant or variable time. This in fact leaks some information about the error terms. Attackers can use side channels to exploit this leaked information to attack the crypto system. There are in fact very efficient and practical side channel attacks on lattice-based signature schemes that exploits this vulnerability of discrete Gaussian samplers. Of course, there are some simple countermeasures, but they perform poorly in practice or do not provide adequate security. In fact, sampling efficiently and securely from discrete Gaussian distribution has been an open problem for a long time. Now, in our work, we observed that since DDG is a tree, there exists an unique path from root to each leaf node. This implies that each sample is generated by a unique input random bit string. Now notice that as a single sample value can occur in multiple leaves, this implies that there is a many-to-one mapping between the set of input random bits to the set of output samples. In other words, we can express each bit of output samples using a Boolean function of input random bits. For example, here the most significant bit of a sample is 1 when the sample is 3 or 2. These samples are generated only when the input random bit are as shown here. Or in Boolean, we can express S1 as shown. This expression sets the MSB 1 only when it receives the above input bit strings. In general terms, we can generate each sample by m Boolean expressions with n variables. For different input random bits, any of these expressions takes same time to execute. Now we can calculate each bit of a sample by executing these expressions one by one, and this leads to a constant time sampling, as irrespective of the input, these functions take same time to execute. But if we store the random bits in an array and use them to generate each sample, the overhead for unpacking the bits and calculating the Boolean expressions become too high. Here we of course get a constant time sampler, but the performance is very poor. Instead, we use the fact that modern processors have wide word length and bitwise Boolean operators. So instead of using single bits in calculating Boolean expressions, we can pack multiple bits in a wide variable and use the bitwise Boolean operators to calculate the Boolean expressions as before. In this example, we assume the processor has word length k and variable var I holds k numbers of ith input random bits. These variables are then fed as input to the Boolean expressions, and we get m variables where ith variable s prime I holds ith bit of all k samples. Now we can unpack these variables to get the actual samples. In this way, we can generate k samples in a batch. Of course, this method has some overhead in packing and unpacking the bits, but that is very negligible. So, in conclusion, in this paper, we provided an efficient and secure method for discrete Gaussian sampling, which was an open problem for a long time. This method can be used even in resource-constrained or small devices, as implementing this method doesn't require any special instructions or large memory. We tested this method with a discrete Gaussian distribution with sigma approximately equal to 6.15543, and this method turns out to be 2 times faster than the best known solution. The complete side channel analysis and an efficient hardware implementation is available in the paper. Here are the references which I used in the talk. And with this, I conclude my talk, and I thank you very much for your attention.